Hello physics students. Today we're going to be using Gauss's law to find the electric field of an object with a non-constant charge density. So what do we mean by non-constant charge density? So suppose I had a sphere like this. This is a tennis ball. Obviously it's hollow, but let's suppose it's a solid sphere. And I take a needle and I stick it in and I extract a little millimeter cubed out of the center of the tennis ball. And then I take a millimeter cube somewhere, extract it from some other part of the cube. For a constant charge density, those two little millimeter cubes would have the same charge, the same number of coulombs in them. But today we're going to look at how to find the electric field if those little cubes I abstract have different charges. In other words, the concentration of the charge varies throughout the object, and in today's example, throughout the sphere. So that's what we're doing today, Gauss's law and non-constant charge densities rho. So suppose we have a charge density function now like this. This is some coulombs per meter cubed, but then we multiply by some number other than 1. And you can see that at radius 0, then the function is just rho 0. But at radius capital R, the outer edge of our sphere, we have capital R over capital R, which is 1. 1 minus 1 is 0. So that means in the middle, the charge is the most concentrated, and then it gradually gets less concentrated outward. That's what I'm showing schematically with this diagram. If you were to take a little cube out of the center, you'd have a lot of charge. Take a little cube out of the outer edge, and you have less charge, and in fact, the charge density on the outside is 0. So what I want to do is determine the electric field for R less than capital R, in other words, inside this sphere, and then for R greater than capital R, outside the sphere, and then after that, I forgot the letter B. Okay. Determine the voltage at the origin. Remember, voltage is the electric field integrated from infinity, R infinity, in other words, from outer space all the way into that point. That's what I want to find. Okay, so next what I'm going to do is, so what I have to do is to get the electric field, I'm obviously going to use Gauss's law. So first thing, to find the electric field inside, I need a Gaussian sphere inside the larger sphere. So this is the surface over which I'm applying Gauss's law. I write out Gauss's law as always, and then the second line, even though the charge density varies throughout, I can still simplify this to E times area because it's still radially symmetric, so the electric field points outward everywhere and it's constant along that surface. So that's why that integral simplifies to just E times the surface area of a sphere. But the problem is Q enclosed is, we cannot use rho times volume because the rho, well, which one would we use? The one at the center, the one in the middle, one at the edge? It's a function. So this no longer works. All right, so before I explain how to solve that problem, I want to just introduce a little pause to allow you to catch up if you need it. Okay, so going on. So how do we calculate this Q enclosed? What we have to do is take a little detour. So what I do is I imagine that, so I can't use Q equals rho times volume, but if I imagine a small, very tiny volume over which the charge density is roughly constant, then I can use the concept of rho times volume because the rho is constant over that volume. So what I'm going to do is pick a sphere like this. Okay, and it's a really skinny, thin shell of a sphere. And that has a thickness to it, even though it may not look like it, it does have a thickness dr. So really thin. And because the radius doesn't vary much, going from one part of this to the other, because it's so thin, then I can use the coulombs per meter cubed times the meter cubed, and I'll get the charge just in that little green shell. So expanding that out, here's the rho function at that particular radius. Now, the volume of this shell. In Gauss's law, when we were doing earlier for spheres, we just did the outer volume minus the inner volume was the volume of a shell. We don't do that in this case. What we do is we take the surface area. So this is the surface area. And we multiply by the thickness of the shell. So it's like area times height when you figure out the volume of something. So that's the volume of that shell. That'll give me the coulombs in that shell. But I don't want just the coulombs in just only the shell. I want the total coulombs inside my Gaussian surface. So what I have to do is add up the coulombs of every shell starting in the center of the little tiny shell, plus, 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 plus. What I'm doing, obviously, is I'm integrating. So I integrate that function. Notice I've already sort of gathered up the constants, the 4 and the pi and the rho 0. And then I distributed this r squared to the 1. And I distributed the r squared to this term. I get r cubed over r. And, of course, my dr is still there. So now I need to perform this integral. And so add 1 to the exponent and divide. Add 1 to the exponent and divide. There's my integral from 0 to my Gaussian radius. I plug in the limits. First r Gauss, and then 0 in, and I get my final expression for the Q enclosed inside my Gaussian surface. So I can end my detour and come back to my Gauss's law calculation. So before I do that, let me put a little pause here to give you a chance to catch up if you need it. Okay, let's continue on. We're going to go back here. So I'll make a little room. And so I have right here E times 4 pi r squared. That part does not change. But the Q enclosed is that expression. You know, let me see if that's visible. Looks like it's a little bit too much in the light. So I'll just shift this down a little bit. All over epsilon 0. Okay, so now all I have to do is do a little solving for E. So as you can see, the 4 and the pi cancel. Okay, so what we have is E equals 1 over epsilon 0. And then this r squared makes this r to the 1 and that r to the 2. So I've got my rho 0, r over 3 minus r squared over 4r. And there is the expression for the electric field inside that sphere, you know, within the larger radius. So let me put a pause here in case you need a chance to catch up. Okay, so remember, A2 was to find the electric field outside the sphere. Okay, so I erased the diagram, but now I just create a Gaussian sphere that totally encompasses the sphere here. And so my Gaussian sphere is like this, and I apply Gauss's law. oops, not B, but A2. So I apply Gauss's law to that sphere. So the left side of Gauss's law, once again, becomes E times surface area of a sphere. But this side, once again, we're stuck because we cannot use rho times volume. So we need a detour again. All right, so you would think we had to do this all over again. Imagine a shell, 4 pi r squared dr, and then multiply by rho 0, integrate again. But we've already done that. Right? We've done this. And so what we could do is just change this and, in fact, recycle this formula. So in your notes, you could go ahead and circle this formula for Q enclosed and label this like equation 1 or something like that. And we're going to reuse it. The only difference is if we had our larger sphere like this, and that's the sphere, and so now our Gaussian surface is out here. When we integrate, we don't integrate to the Gaussian surface because there's no charge over here. We have to stop our integral at the surface of our charged sphere. So all we're doing is changing our limit to capital R. So let's go ahead and do that. I'll work up here maybe. Or, you know, maybe I could stick this in down here. So Q enclosed equals 4 pi rho 0 r cubed over 3 minus r to the 4th over 4r from 0 to capital R. And you could write in your notes, this is from equation 1, you know, because you have it circled earlier in your notes. Okay, so let's plug in our limits. Capital R cubed over 3 minus capital R to the 4th over 4R. And then minus 0 minus 0. Okay. Now, this term right here, what we have is R cubed over 3 minus R cubed, oops, make that a little bit bigger in case it doesn't show up on the screen. So we have R cubed over 4. And we can combine those with a common denominator. If we multiply this by 4 over 4, we get 4 over 12. And this becomes 3 over 12. And when you subtract those, you get 1 over 12. So this becomes 4 pi rho 0 r cubed over 12, which we could then make this 1/3. So we have 1/3 pi rho, oops, not p, rho 0 r cubed. Okay? So that's the Q enclosed. And we can now go ahead and end our detour. And go back to our Gauss's law calculation here. So let's plug that expression into Q enclosed here. Okay. And as you could see, the pi cancels out. And then we've got the 1/3 divided by 4 is 1/12. We can write our final expression for the electric field outside this sphere as 1/12 epsilon 0 rho 0 r cubed over little r squared. Okay, so if you need a moment to catch up, I'll create a pause here, give you that opportunity. Okay, so I didn't do a unit check earlier on the formula. Let me do that now because I like to do that all the time. It's a good check. So remember, we need units of here, K coulombs over meters squared from KQ over R squared. Is that what we have? Well, we have the 1 over epsilon 0. That satisfies the units of K. Rho 0 is coulombs per meter cubed. Then I have meters cubed for the R cubed all over meters squared. And you can see these meters cubes go away, and I do indeed have the right units for this formula, so it looks like it has the right form at least. This formula, well, I have 1 over epsilon 0, which is my units of K. I have rho 0, which is coulombs per meter cubed. And then I have meters here, meters squared over meters. So all of this is just meters in the parentheses. And you see, it looks like we have the right form. Again, we might have lost a constant somewhere along the way, but the formula appears to have the right form. All right, so before I go on to the voltage at the origin, which is part B, I just want to quickly sketch a graph. So electric field, radius. And the big transition is at the surface of the sphere. This is inside the sphere, outside the sphere. This is the formula inside the sphere. Notice at radius 0, the electric field is 0, so it starts here. And then we don't even need to take a second derivative because this is pretty simple. It's like a x squared, so we have like r minus r squared. This is a downward parabola. You could do the derivative twice and see that it's negative, but a downward parabola just goes like this, rises to some peak value, and then after, when we go outside the surface, we have all constants over r squared. So we have so at 2r, for example, we have not a half, but a quarter of the electric field, and it goes down like this. We could even write proportional to 1 over r squared here. The peak value, easiest just to plug in capital R over into this formula, and what we get is rho 0 r over 12 epsilon 0. Plugging in capital R right there and doing a little canceling. So that is the electric field, okay? Last thing, voltage. So yeah, you need some space here. Oh, okay. All right, so if you need some time, I'll create a pause here, give you a chance to jot that graph down. Okay, so part B. So V at r equals 0. So what we have is a sphere like this, electric field in here, electric field out here, okay? So what I have to do is to find the voltage, I'm integrating from infinity into some point of the electric field. So there's the general expression, the concept of what voltage is. So you have to realize we have one formula for the electric field out here. We have another formula that I erased the electric field inside. Then what we have to do is we have to split this integral into two parts. Integrate from infinity into the surface using that electric field expression. And then from the surface in the rest of the way, we have to integrate with the other expression for the electric field. So this voltage will be minus the integral from infinity into the surface of the sphere of the electric field function outside, dr, and then picking up the integral from there, a little messy, okay, from r into the origin of the electric field inside, dr. So the next step we have to do is take this expression, put it right there, the expression I erased, put it right there, evaluate the integrals, plug in the limits, and solve. But I'm not going to show you that detail today because I don't want to get bogged down in details. Today I just want to emphasize integrate from infinity in means you have to break the integral into two parts and then you evaluate both those to get the voltage at the origin. Okay, so that's it for our example problem. But I do want to just now summarize this electric field for non-constant charge densities, because we only did spheres today, but you can have non-charged density for, I don't know if I created a pause, I don't remember, but if you need to, then I'll pause here and give you a chance to write this down. Okay, so you can have non-constant charge cylinders. The charge might be more concentrated in the middle, get weaker on the way out, like we saw in our example problem, or maybe it's the other way. Maybe it's no charge and then it gets stronger concentration as you go outward. Whatever the function for rho is, you will have to, the key idea is in Gauss's law, you get to that second line, E times area, and then to get Q enclosed, you've got to perform an integral for cylinders also. So let me just kind of show you how to do those setups for Q enclosed. So you get to E times area equals Q enclosed over epsilon 0, the second line of Gauss's law. Derivation, this is going to change depending on sphere or cylinder, but for a sphere, you get Q enclosed by integrating from 0 to r Gauss, or possibly to the edge of the sphere, depending on, but you take your rho function and you multiply by 4 pi r squared dr. So that's the dA for a sphere. This, the dV, the tiny little volume of a shell. For a cylinder, Q enclosed, again, you're integrating either from 0 to the Gaussian surface if you're inside the cylinder, or if you're outside the cylinder and you want to find the electric field out there, you're obviously going to stop at capital R or whatever the radius of the cylinder is. So you're going to have your rho function. Again, it might be like what I had with the rho 0, 1 minus R over R, something else. It could be something else. But the surface area, or the volume over which you integrate, will be the surface area of a cylinder times thickness dr. So the surface area of a cylinder is 2 pi r circumference times the length. So that's length times width of this cylinder, right? This side of the cylinder is 2 pi r, and the other side of the cylinder is L when you open that up. So surface area times the thickness of this shell dr. So again, this will change, but that other part dV right here, that is always the same when you're calculating Q enclosed. And you could also have, yeah, I guess for the plane, I've never seen a non-constant charge density, yeah. I guess I'll leave it off because, again, I don't think those examples ever come up. I can't think of any. So here it is, rho times dV integrated over out to the Gaussian surface. All right, so that's non-constant charge densities. The left side of Gauss's law, always the same, even in this case. But now this time, to get Q enclosed, we actually have to perform an integral, right? With Gauss's law, it was always just E times area. That was easy. You didn't actually have to technically integrate anything. Now we've got to perform an integral to get that Q enclosed. All right, I hope you enjoyed this video. I'll see you in the next Gauss's law video.